Good morning, students. In this video, we'll go for the new technique of particular integral, which is method of undetermined coefficients. In this method, we have three possibilities for solution. And so, in this video, I'm going to cover the case one. So, basically, this is a technique for particular integral as a part of general solution of higher order differential equation. So, let us begin with our usual consideration of second order differential equation y double dash plus c1y dash plus c2y equal to rx, where c1 c2 are arbitrary constants, y is depending on x, y dash y double dash they indicates first and second order derivatives of y with respect to x respectively. On the right hand side we have r of x as a random function of x. Again, the first step is to define differential operator, that is d, and this will be d by dx. So you can understand, if I take d raised to n, it indicates the nth order derivative, and therefore the second order differential equation will take form d square y plus c1 dy plus c2 y equal to r of x. Separating for y, it gives me d square plus c1d plus c2 times y equal to r of x. Now, considering this big bracket d square plus c1d plus c2 as a random combination of d as f of d, the equation will take form f of d times y equal to r of x. The next step is to consider particular. Now, as I told you, there are three main methods: direct methods or special functions, which are already covered in our previous videos. Second method is method of undetermined coefficient. This method we are starting in this video, and later on we'll also see method of variation of parameters. Now, let us start with first example, that is y double dash minus 2y dash plus 5y equal to 5x square minus 6x square plus 6x. First step is to consider operator form. An operator form is f of dy equal to rx, that is d square minus 2d plus 5 times y equal to 5x square minus 6x square plus 6x. Now, for complementary function, I am taking auxiliary equation f of d equal to 0. For this equation, we have complex roots 1 plus or minus 2. So, alpha is equal to 1 over here. By mistake, it is written 0. It is alpha equal to 1 and beta equal to 2. And therefore, complementary function will be c1 e raised to x cos 2x plus c2 e raised to x sin 2x. I have taken this e raised to x in multiplication with this 2. There is a special role of this part, that's why I am writing it like this. Now let us move to particular integral. Now, this is how the method of undetermined coefficient will start. For particular integral, consider the differential base is capital B of Rx. Over here, Rx is a polynomial function 5x cubed minus 6x square plus 6x, and therefore I need to take differential basis for this function. Now, what do we mean by differential basis of this function? It simply means that how many variable components are required to generate this function and its all possible derivatives. So for that, let me take this function first of all. So if I look carefully, it is with three variable components: x cube, x square and x. Now if I take derivative, it will give me x square and x as a component. If I take one more derivative, it will give me x and constant. And finally, if I take derivative, it will give me constant, and later on all possible derivatives will be 0. So the main motive is how many variables and constants we require to generate all possible derivatives along with this function. So it is x cube, x square, x and 1. Now, before fixing this as a valid differential basis, I need to check whether there is any repetition of this component in complementary function or not. This is the reason why I considered my complementary function as this. Now see, the first part is e raised to x cos x and second part is e raised to x sin x. So I will check whether any of these two is coming into differential basis or not. Fortunately, there is no repetition in between these parameters, these values and elements of complementary function. That means this is valid differential basis. Once we have non-repeated differential basis along with complementary function, we can formulate our particular integral, and that is nothing but ax cube plus bx square plus cx plus d. So in this technique, we are formatting our particular integral first, and later on we are eliminating all these undetermined coefficients. So the method is known as undetermined coefficients. I'm repeating once again. My function is for x cube 5x cube minus 6x square plus 6x. I'm taking differential basis as x cube, x square, x and 1. These are the elements which can generate this function and its all possible derivatives. Check whether there is any repetition with Rx or not. As there are no repetitions, I am considering this as a valid differential basis and formatting my yp. Now the next step is to find values of a, b, c and d. D. So we know that yp is a particular integral of differential equation, so it will also satisfy given differential equation. Now, looking at the given differential equation, it contains second order derivative, first order derivative. So, I am finding first of all possible derivatives required for the given equation. Y is ax cube plus bx square plus cx plus d. Taking its derivative will give me 3ax square plus 2bx plus c, and y double dash as 6ax plus 2b. Now, considering all this y dash, y double dash into the left hand side of differential equation, and it will give me 6ax plus 2x. This is the neighborhood value of y double dash minus 2y dash, that is 3ax square plus 2bx plus c plus 5 times y ax cube plus bx square plus cx plus d equal to right hand side of the equation. Now I will collect all different powers of x and then I will compare both sides for a, b, c and d. So if I separate equation on the left hand side as a coefficients of x cube, x square, x and constant, my both sides are now comparable. So 5a is equal to 5, which gives me a equal to 1. Minus 6a plus 5b is equals to minus 6, which gives me b 0. 6a minus 4b plus 5c is equals to 6, which gives me c is 0. And 2b minus 2c plus 5d is equals to 0, which gives me d equals to 0. So I have LU of A, B, C, D as 1, 0, 0, 0, 0 that I am taking into YP. That gives me value of YP as x cube. Combining this value with complementary function gives me general solution. Let us consider one more example. Y double dash minus y equals to sin x. So operator form is d square minus 1y equals to 5 sin x. I am taking f of d equals to 0, so it gives me two roots, 1 and minus 1. And therefore, complementary function is c1 e raised to x plus c2 e raised to minus x. Now, considering the right hand side of the equation, it is sine of x. Now, what are the derivatives, possible derivatives of sine x? Derivative of sine is cos x derivative is minus sine x derivative is minus cos x derivative is sine x. So there are basically only two variable parts, sine and cos. So this is the differential basis of this function. Now, checking whether there is any repetition with CF or not. So CF is e raised to x, e raised to minus x. There are no repetitions with this sine and cos. Therefore, we can consider this as a valid differential basis. Once we have valid differential basis, we can format our value of yt, which is a sin x plus b cos x. Now, Rest of the calculation is to find values of A and B. Now, as given equation, it contains y dash and y double dash. I am assuming that yp, our assumed value a sin x plus b cos x, is the solution of given equation. So I have to take y dash as a cos x minus b sin x, y double dash as minus a sin x minus b cos x. Taking all these values into the given equation will give me minus a sin x minus b cos x minus a sin x plus b cos x equals to, I need to write down this into elements of differential basis. So it is 0 cos x plus 1 sin x. Now, considering all values of cos x and sin x together, it gives me minus a into cos x plus minus b into minus b sin x equals to 0 into cos x plus 1 into sin x. Comparing both sides, the coefficients of cos x will give me minus 2a equal to 0, which leads to value of a equal to 0. Minus 2b equal to 1, which will give me value of b as minus 1 by 2. Now, taking this value of a as 0, b as minus 1 by 2 in yp, my final value of yp will be minus 1 by 2 sin x. Combining it with complementary function will finally give me answer minus 1 by 2 sin x. This is how the technique of method of undetermined coefficients will work. It is not that you have to use this method compulsorily. There are direct methods also which are applicable parallel. For both of these examples, I would like to give you one exercise, that is, find answer using direct method also and then compare your solution with the method of undetermined coefficients. In exam, you can select any method until it is mentioned in the question. I hope this method is clear. We need to be careful about two steps only. The first step is how to find differential basis, and the second step and the most important step, that is whether there is any repetition into the part of CA formula. Go through both examples once again, pause and ponder whenever it is